Welcome. In this video, we'll learn about pulleys, which is one of the greatest inventions of human race. So, before we go into pulleys, let's see what was the old way of dealing with loads. So, in the old days, if you have a load, you just use your muscles, lift it up. And you can see here, you're comparing between S, the effort force, your effort force to pull the load up. So from equilibrium, S would be equal to F. So now that's before the human invention of pulleys. So pulleys are just like wheels that you have cables or ropes roll around it to transfer forces. So let's see this setting here or system of a fixed pulley. So fixed means it's fixed to the ceiling and it's pinned to the ceiling, and then you have the rope going around it, and you basically lift the load by pulling the rope down so it rotates around the pulley and pulls the load up. So if we analyze the free body diagram of the pulley, and we very carefully here draw the rope or the cable around the pulley, and from one end it feels F, which is the load, and in the other end it feels your effort force pulling down. From observation, we can say that the force at both ends of the cable, it's the same cable, that moves around a pulley that's free to spin. So the force is the same at both ends of the cable, or even if you cut the cable at any point along its length, you will find that the internal force is the same. So that effort force would be equal to the load force in this case. So in this case, the pulley didn't really help in terms of reducing the effort force that you want to put in to lift the load. It helped in changing the direction of the force that you need to lift the load. So instead of the first case, you need to pull it up. So you just, depending on your own, muscles, shoulder muscles, and it's a good exercise, but over time it's not ergonomically kind of friendly. So now you're pulling down, so you lift the load up. So now you can actually use your own weight, and it's more easier to do that. So, but the force is still the same. The input force, what we call the input force, is equal to the output force. So let's see another use of the pulley. But before that, of course, another thing here is you have to be careful about supporting that pulley in a strong way, because now this ceiling connection needs to carry double the load you're trying to lift, because the load itself is pushing down and you're pushing down also. So kind of the pulley is resisting to double the forces here. So the other way of using the same pulley is making it movable. So the cable that's going around the pulley is fixed at one end in the ceiling, and then you are actually now pulling up. So your force, your effort force is going up. If you draw the free body diagram, again, be careful about drawing the cable around it, and we know that the S in this case is equal to the reaction force. So that's actually here a typo. I will fix that right away. So here, this one here should be the force S, the effort, and then R is the reaction force of the ceiling. That also is the force inside the cable, and like we learned before, it's the both ends here are for the same cable, so R is equal to S. So by fixing now the free body diagram, and I see here that the load force F is going down, so from equilibrium now I can see that the effort force that I put in that system is equal to only half of the load that I want to lift. And now this is a smart way of using the pulley. But it's still, you're lifting up, so you're depending on your own forces or muscle forces instead of your kind of capitalizing on your own gravitational load or weight. But I mean, you can't get everything, right? So another way of using pulleys is using combined pulleys. So instead of limiting ourselves with only one pulley, we'll use multiple pulleys. So there's this setting here. We'll not do the detailed free body diagram for this system, and we'll leave it for the class time. But if you solve the equilibrium of the two pulleys together, you'll find that the S force would equal to also half of the load that you're trying to lift. But it's better than the previous case because now again the direction of the force you're applying is downward, so you can actually use now your own weight, so it's ergonomically better than the previous case by using two pulleys here. Another way of using these two pulleys is changing the way that the cable goes around the pulleys, and also changing the way that the pulley is supported to the ceiling. So if you solve the free body diagram, and we'll do that in the class time, you will find now that the input force that you put in is getting smaller. It's 1/3, not half of the load that you're trying to lift. But again, you're not getting the ergonomically better situation compared to the first case of the combined pulleys. And you can go even like more fancy here by increasing the number of pulleys. And in this is the setting of blocks and tackles, and this is a common pulley system that's used in hoisting loads and cranes, and so you can multiply now the effective pulleys and that will result in reducing the force that you're applying here, the effort force S, to be a fraction of quarter of the load. Here, you know, we will do the free body diagrams again so you can verify and understand more what's happening here. But pulleys are really amazing mechanical systems, and it helps to make the job more ergonomically friendly, and also reduce the input force relative to the output force. So that's the end of this video, just explaining what are pulleys and how they function. And the main thing here is that trace the path of the cable around the pulleys, because at any point along the length of this cable, the force is the same. The internal force will be the same. So that's the advice that we'll see in the next video, how this applies in an example of a pulley system. I will see you in that video. Take care, and thanks for watching.